Alrighty, part 2. We're looking at friction and how friction plays a role in Newton's laws of motion. So you have two types of friction. You have static friction, which an object is moving, and then you have kinetic friction when an object is no longer in motion. One thing I'm going to do is go ahead and turn back on some of my settings, make sure we're on the correct color, and then now we're going to talk about how we calculate friction overall. If you notice on your reference sheet for AP Physics that says that a frictional force, the absolute value of a frictional force is going to be greater than or equal to, actually nope, that's less than or equal to. So it's going to be less than or equal to mu times the absolute value of force normal. And that's because when it comes to an object, if I just start to push the object, but it takes 10 newtons of force overall to overcome friction, if I push with 1 newton of force, but it's still the maximum is going to be 10 newtons, there's only going to be 1 newton of friction fighting me back. If I get 9.9 newtons of force applied, 9.9 newtons of frictional force will be fighting against me. So if I hit that magical number of whatever it is for your object, then motion starts to happen. That's why it's represented like this in your reference sheet. So back to static and kinetic. If an object is not moving, it tends to have a larger amount of frictional force you need to overcome it. So what you get is this coefficient of friction tends to be, for static friction, always tends to be larger than the coefficient of friction for kinetic. And that is the reason it always takes more force to get an object starting to move than it is to keep it moving. So usually these two numbers are going to be a little bit different. Mu is so we're going over here, we'll do a little side tangent, talking about this formula a little bit more. Mu is a unitless number. Is a unitless number. And that represents, because this is a ratio of proportionality on how much the weight of an object is, or its force normal usually, and compared to how easy it would be to push it. So it's often force applied is proportional to weight of an object. And then this could be written as the coefficient of friction is proportional to often force of friction over force normal. So that's where this proportionality comes from. Newtons divided by newtons gets you a unitless number. It's just a ratio. Usually that number is going to be anywhere from 0 to 1. So mu. Typically, it's going to be from 0 to 1. If it's greater than 1, then that means your object is easier to pick it up than it is to push it. So going back to the coefficient of frictions, this is for static friction, that'd be the force required to get the object to start moving. This is the force required to keep it moving. So these two formulas look very similar. Let's go ahead and change that color up for me. And let's do that frictional force frictional force static friction would then be mu sub s times force normal. And then for kinetic friction, it's going to be looking very similar. Now, one last thing I want to talk about is what happens if, for static friction, the force applied is greater than the force of static friction. Well, that's when the object then becomes in motion, and so then you hop over to using kinetic friction. What happens if force applied is less than or equal to the force of friction, force of static friction? And actually that was written a little bit wrong. Let me erase that real quick. There we go. So the force applied is less than or equal to static friction, then you're still going to have no motion. All right. no motion. However, when I hop over here, what we have is once force applied, once the object is moving, is greater than kinetic friction, the object is then going to have an acceleration that is positive. All right. If force applied is less than or equal to the force of kinetic friction. Oh, did a little boo-boo there again. If force applied is less than kinetic friction, your object is often going to slow down. So acceleration is usually denoted as negative here. If force applied is equal to kinetic friction, then your object is then going to be hitting a constant velocity. Alrighty, so that's what we have so far. We've talked about Newton's first, second, and third law of motion. We've talked about friction. Now I'm going to go on and make a third video talking about some of the special examples that we talked about in class.